Good morning, everybody. So we'll continue the financial data analysis using the MATLAB. So these are the common patterns we often observe from the financial data. So trend, seasonality, and correlation or serial correlation. Right? So mostly you can just use a decomposition of, or we're going to break down the time series, okay, according to the possible patterns inside it. So let's say the overall data set for the time series is YT. Normally we can have three components: seasonality, trend, and also um, the remaining item is so-called the arrow terms, okay, or the remaining components. So in this case, you can just have an additive model by adding the sum of these components. For example, the YT is equal to the seasonality plus the trend plus the remainder components. Let's say you can just put epsilon t or et in this case. Okay, so this is in the addition form. Therefore, we have an additive model. So for multiplicative model, you might end up to have yt equal to st multiply tt, then multiply the epsilon t or error terms are so called, right? The error terms. So uh, you can actually having a additive and multiplicative models, okay, of a time series yt in this particular form, right? So you can get rid of the trend and seasonality, okay? Get rid of the trend and seasonality. So for this one basically have a trend now. So this one might have overall they might have a downward trend in this case. So for this one, you have a trend plus the fluctuating up and down, which will consider as you actually have a trend, but somehow the value is moving up and down. So this up and down basically is contributed by the ET components. Okay, ET components. So the last model actually have trend, have seasonality. Okay, trend and seasonality, and also you can see that the values of the seasonality for every year is increasing. Okay, it's increasing. Okay. So we can most probably we can use a so-called difference operation, okay, to obtain the series we want. Okay, so the first one we call it the difference operator. So if you operate this to a series, let's say yt or xt, then you end up to have xt minus 1. I think this is something you're quite familiar for finance student. You have the changes of if the xt basically is the price index. Let's say xt is the price index. Then most probably you have a changes of price index here. Okay, so beside the difference operator, you can actually include the backward shift operator inside the equation. Right? So the difference between this operator must operate on a series or time series. So this will actually shift the xt by leg 1 behind. Okay, so this is what happened. So in short, if you want to see the relationship between the difference operator and back shift operator, so you can just rewrite the equation in this particular form, which is the leg of a difference operator. So you know that the xt basically is bt minus 1 leg 1 is actually the back shift of xt. Okay, so this one we can just rewrite it as the 1 minus the back shift operator on xt. Okay, so you can't write, the order is important. You can't have something like this. The operator must operate on something, isn't it? So it is not right to write this form. So then this is basically the operator of p operate on xt. Okay, so Therefore, the B itself is meaningless unless there is a series inside. So if you have a xt minus 2, we also can relate this to the B of shift the xt minus 1 time, then you will get xt minus 2. So also xt minus 1 can be written in a backward shift operator by bxt. Okay, bxt. So in short, we have a b so-called power 2 xt, which is operate the leg by twice. Therefore, instead the xt will become xt minus 2 in terms of time. Okay, so in general, you can say that the back shift operator or backward shift operator operate on xt by j times, then we have a xt led by j. Okay, xt led by j. So this differencing operation actually can changing the train become a so-called stationary or random process. Okay, so if you have xt, you operate on using the backshift operator or difference operator on it, then you have xt minus xt minus 1. So there's a train here, but eliminated by the difference operator, then you can see this is more like a random process at the end. Okay, so because in most of the series or time series involved, we need to make sure that your data set is stationary. Okay? So in that way, you can actually put in the stationary models in your data set. Why this is important? Because if your data set have a non-stationary behavior, then let's say the mean of your model xt will go to infinity as t go to infinity, or your standard deviation or variance of xt will tend to go to positive or negative infinity. Let's say positive infinity when the time approaches infinity. Then in real application, we are not allowed, or we actually can't deal with infinity terms involved. Right? So therefore, we need to make sure that our data set is stationary. Stationary in terms of what? In terms of the statistical property like mean, variance. Most probably, we are more interested to know the weak form of stationary instead of the strong form, or just that we just investigate the first moment and second moment, which is the mean and variance. Okay, or covariance, which is enough for us to have a weak form stationary for our time series. Okay, this is important in the modeling parts afterwards. Okay. But somehow in this study, we are more interested to analyze the so-called serial correlation in the time series. Okay, that is our concern. So we have first we introduce the so-called white noise. Okay, so white noise is normally distributed. Most probably it should be a normally distributed data set xt where the mean is 0, so it fluctuates around 0 and the variance is constant sigma square. Of course, the variance is a constant. Somehow it can be non-constant and involved with the heteroscedasticity effect in your models. Okay, so first of all, we have a white noise. So the white terms come from analogy of white light. So the white light consists of 7 colors. So all those, you do an experiment, then you combine all the lights and then you twist the circle very fast, you end up to have a white color, isn't it? So this is the analogy to that. So that means it consists of all possible periodic oscillation with different lambda. Okay? So basically the white noise is, so the noise basically is a random process. Random. So this random process can be independent or non-independent. So in the next section, we're going to look at two types of models where it can be used to capture the serial correlation of a time series. So moving average process. So if you have a so-called moving average order 1 process, let's say you have X. So XT can representing the price, the returns, or even volatility. So the XT is basically equivalent to data ZT minus leg 1, this one plus the error term. So ZT basically is a white noise, or it's a random process. So in this case, you can see that the XT is depends on not only the noise at time t, but also t minus 1. So how strong the leg 1 noise is going to influence the XT. It depends on the data. Okay? So data, let's say, can be 0.1, means 10%, okay? 0.9, 90% of the leg 1 ZT is going to influence the XT. Okay? So the leg 2 basically is going to increase the leg order 2, let's say. So you have XT. So here you can use data 1, ZT minus 1, plus data 2, ZT minus 2, plus ZT. Okay, in this case, there's no constant involved, means that your series is basically is not start from this one. Start from 0 basically. Then the fluctuation will be something. So of course, if you plus, let's say plus data naught, okay, this one plus the data naught of both the equation, then this series will actually shift. This series will actually shift to, let's say, if data is 0.5, then it will shift to 0.5. So the data will fluctuate about the 0.5 level. So let's say if data is 0, data 0 is 0, basically will fluctuate around 0. Okay, because let's say if the white noise is with 0, most probably your data set of data naught will be close to 0 as well. Okay, guys? Okay. So for autoregressive, from the terms regression, basically you have an X regress of Y. Okay? So your AR1, autoregressive model order 1, is going to have XT. So not only the ZT, now the XT depends on its own series with the leg of 1 and the noise as well. Right? So there are two terms influence the XT now. Okay? For example, yesterday returns is depends on today's returns, present one. It depends on yesterday returns t minus 1. Okay, and the noise is something that we do not know what is the cause and the reason of the fluctuation up and down. So we just put ZT to include all the possible factors or impact that influence the XT. Okay, so for order 2, then you're going to have 2 legs XT. So you have a phi 1 XT minus 1 plus phi 2 XT minus 2 plus ZT. So you're going to have not only leg 1 but leg 2 as well. Okay? Influence so not only yesterday but 2 days ago's information is going to influence the XT. Okay, so in stock market, normally the impact might go to weekly, monthly, or even like COVID-19, the impact will be much more significant over the time. Maybe even after 2 years or 3 years now. Okay, 2005, so 2022 until now. So the impact might be still there. If you heard any global flus pandemic again, then the impact of COVID will be, come back again. Okay, guys. So now we're just trying to okay. So now I can actually combine two of these AR1 and MA1 become the so-called ARMA leg 1, order 1 and order 1. Okay. So the first leg is actually referring to the AR. The second order is actually for the MA models. Okay, so you're going to have the so-called So when you combine these two, basically you're going to have an xt minus the phi of xt minus 1 equivalent to the zt plus the data of zt minus 1. Okay. So for this case, you don't actually equate these two. Basically, this is AR1, this is MA1 components, isn't it? Okay. So ZT basically is the common component for both of them. Or you can just write xt in terms of phi xt minus 1 plus data zt minus 1 plus zt. Okay, so this will be the ARMA 11 model. Okay, ARMA 11 model. Okay, so we have three models: pure MA, pure AR, and combination of AR and A, which is the so-called ARMA model. Okay, so we're going to run a simulation. Let's say the pure MA, pure AR, and the AR1 models. Okay, using the method. So here we can just create a new script. Okay, so new script. Let's say this is a new script. Let's say we want to save this script. Okay, save the file. So we're going to put it in the, let's say I'm going to put it in the MATLAB folder called MATLAB class. Okay, so this is simulate ARMA. So .n file, which is a MATLAB file. So then this is the file we have. Okay, now there are several functions we're going to use here. Okay, several functions we're going to use. So we have, we're going to look at one by one. Right? So first of all, we can just put the statement. Let's say simulation simulation AR1 mode. Okay. So in this case, we can have. So let's say our first model, you can just put any number, but MATLAB, the first variable must be an alphabet, cannot be number. Okay. So you have model 01. You cannot put 01 model. Okay. Then you're not able to save it as a variable. So let's say the first model, let's say we start with MA. So since the nodes start from MA. So the first model we have, I think we include the MA also, 01. So we have first model. So we're going to put the specification of the model, which is ARIMA. So we just refer back to this equation. So the data, if you do simulation, the data must be provided. Let's say this data. The ZT, basically, we're going to generate the random numbers to get the ZT. So the ARIMA model consists of, so what is the constant? So the constant basically the data not. So the constant we set it as 0. So if you put any numbers, then the movement of your series will shift up and down only. Okay? So then the MA component, the MA coefficient. So let's say we just put, let's say 0.1. Okay? 0.1. So then also the variance of your equation, how the dispersion of your values or observation to the average value 0 for this case. Okay? So this one you can just simply put a small value, should be enough. 0.001, I would say. So this one you can alter the value afterwards. Okay? Then we can just put a random number. So because the ZT should be a random number, so we just use the ZT. So you can use the default value. So you're going to generate the, this one is the default. So therefore, every time you were able to generate the same random number in this case. Okay. So your MA01 model or MA1, make it simple. So now we're going to simulate, calling the simulate function. So what model is going to simulate? So this is the model we have construct just now, right? With this ARIMA specification. So this is our model MA01. Okay. Then how many numbers are there? So in the previous data analysis, the MYSE consists of 3027 observation for returns. Okay, so this is the returns we're going to simulate. So we have 3027 observations. Okay. So then we're going to plot the graph. So just plot the MA1. MA1. Let's say we put the title simulated MA1. Okay. Of course, the data is 0.1 because you can just change this value afterwards. Okay. So now we can just run this, go to editor and run. So you can see there is a MA1 models with the values, of course, display here as well. So if you highlight this, you will see this is a simulated values, everything close to 1, which is normally distributed. So this one is the models, basically. Okay, so I think we can just to save some space. Maybe we can just have a format compact. So this is just to save some space. Now we can just run this one more time. Okay, so this is a simulated MA1, okay, with data 0.1. Okay, data 0. So the equation basically is equivalent to this data 0.1. Then we have xt generated. It seems like a random process. It seems like a random process. Okay, seems like a random process going up and down. But there is a serial correlation involved, okay, in this series, which is not easy to observe. Okay, which is not easy to. So look at the specification of the model. Okay, you have AR10. So this is 0 here means the AR. 0 here means the integrated. Okay, so if you have data with non-stationary or train, then the I should be 1. Okay? So these are the specification, and the MA coefficient is 0.1, okay, variance is 0.01. So this is the specification of the model. So then if you look at if you want to simulate the MA2, let's say this model here, then you're going to specify what is your data 1 and data 2. Just now we have data 1, which is 0.1. Okay? Or you can quickly run this by changing the 0.1 to 0.9. Then let's see, you can observe any differences between. Basically, it's almost the same, just that the fluctuation limit, upper limit and lower limit might be slightly different. Okay, so let's say this one just refer back to 1. So now we can go for the second model. We're going to simulate. We're going to simulation for MA2. Okay. So basically everything remains the same like this, or you just copy and paste. So now the ARIMA model, let's say this is the second model. Now constant remain as 0. So the MA1 consists of two values, isn't it? The coefficients. So we can just use the open bracket and close bracket. Let's say MA1 is 0.1. The data 2, let's say 0. Let's say 7. Just close. So you have two MA1, data 1, data 2. Specification, data 1 is 0.1, data 2 is 0.7. Okay. So let's say we remain the variance, use the same random numbers. So this is MA2 now, okay? This is MA2, this is MA2, this is MA2. So just change the value inside, then now you can have a look at the possible value. So just run this one more time. Then this is your MA2. Basically, there's not much difference, just that the fluctuation values is also close. So this one actually go up to 0.1. This is go up to 0.15. Okay? So because you have the second component influence the result. since the random number is the same, therefore the simulated diagram also the same. If you don't use the RNG by default, every time maybe you end up with a different series. So we fix the set of random numbers we're using. Or you can use the RNG with different seed number, and then you have different types of different set of random numbers. Okay, so simulated MA1 and simulated MA1. So now if you want to compare this with the actual series, so in the starting analysis, we actually let's say we want to compare with the actual series. Let's say this one, just copy and paste this. So we're going to look at the NYSE again. So this is the NYSE series, return series. Return series. So you just call back this one. So let's say we clear every time. We just will clean up the values, clear in the not only the workspace and also the command window, both of these. Therefore, the latest value will be. So we just load the data. You still remember this in the early class. Equity IDX. So load this one, then you have price of NYSE, isn't it? So this is from the data table, if you still remember. .NYSE. So another series is the Nasdaq. Okay, Nasdaq. So the return for NYSE using if you use the percentage, then we just multiply 100. Right? Price to returns. This is a function convert the price to return. Then of course we are going to changing the price of NYSE to return NYSE. Then you can just plot the graph, right? Plot the graph for the return NYSE. Then we can do a comparison. So this is the title. Let's say we move down to the title. Okay, now we can compare the simulated MA1, MA2 compared to the actual NYSE return. So let's see how good is the fitting. Of course, this is by just looking at this, okay, so you can see the differences between them. So you can see this is the actual returns for NYSE, okay. Somehow it is what I can say here is the difference between the simulated result and the actual returns of actually any stock market, you might end up to see there are huge numbers of up to -6, up to +4 or 5, isn't it? But the normally simulated models end up to have, as we know, the 99.7% of the standard the values or observation will fall ±3 standard deviation from the mean, which is 0, isn't it? But in the financial time series, we're expecting a lot of extreme values. So therefore, these are, if you cut out all these extreme values up to 2, let's say you cut out all the extreme values after ±2, then this graph basically will look exactly like this. Okay, but somehow in financial data series, you know that these extreme values will make the simulated and actual value looks quite different, okay, due to the extreme values. So how to deal with this? The normal assumption of your simulated value is not what we're expecting to see in the actual return series. So you can use other types of distribution. So in the early part, we have seen that student T might provide more extreme values or heavier tail distributed data as compared to norm. So that might be one of the solutions to deal with the actual or real or actual time series involved. Okay, guys? So this is a comparison between the simulated and the actual return series. The only difference is the extreme values. Okay, it's much more than the simulated value because this is normally distributed. This is the actual value. Okay, guys. So we end the session here. Then the next session we will simulate the AR1, AR2, and also ARMA 11 or 22 afterwards. Okay, guys. Bye bye. Thank you for watching.